Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Welcome back to the show. Today, we're tackling a problem that, if you really stop and think about it, sounds completely impossible.
It really does.
And I don't just mean, hard to solve, impossible. I mean, physically, logically impossible.
It's one of those things we absolutely take for granted in modern science, isn't it? We see the results in textbooks, we see the neat little charts, and we just accept it.
Right? We just nod and say, oh, the sun is 73% hydrogen.
But if you strip away all that modern context and just look at the raw physical reality, I mean, where we are versus where the stars are, it makes absolutely no sense that we should know what we know.
Exactly. So let's start there. Let's set the stage with just the sheer scale of this impossibility.
Okay.
We look up at the night sky, we see all these little pinpricks of light. Even the closest one, our own sun, is 93 million miles away.
93 million miles. I mean, it's a number we can say, but it's not a number we can really feel. Light itself, the fastest thing in the universe, takes over 8 minutes to make that journey.
Think about that. If the sun were to just switch off, we wouldn't know for 8 minutes.
We'd be blissfully unaware, floating in the dark.
And that's our next door neighbor. What about the next one? Proxima Centauri.
Now you're getting into truly absurd distances. That's about 25 trillion miles away.
25 trillion.
It's a number that just breaks the human brain. If you tried to fly there with our fastest space probe, it would take, tens of thousands of years? It's just not on the table.
So the physical constraints here are absolute. We cannot touch these stars.
No.
We can't send a little rover to scoop up a sample of the sun and bring it back to a lab.
Absolutely not. You can't run it through a mass spectrometer. You can't put it under a microscope.
It definitely can't land on them because, they're giant balls of nuclear fire.
Right. The surface temperature is thousands of degrees. The core is millions. It's not a place you visit.
And this is the paradox that's at the heart of our discussion today. We know what they're made of.
We do. And not just vaguely.
With extreme accuracy.
Extreme accuracy is the perfect phrase for it. We can tell you the percentage of iron in a star halfway across the galaxy.
Yeah.
Better than we can tell you the exact mineral composition of the Earth's mantle just a few dozen miles beneath our own feet.
That's the part that gets me. We have a better chemical inventory of the entire cosmos than we do of the deep interior of our own planet.
It's completely backward, isn't it?
It is. So the mission for today is to explore that paradox. How in the world do we know the chemical recipe of something we can never, ever touch?
It's a fantastic detective story.
And looking back through the history of it, it seems like for most of human history, the smartest people on the planet just accepted this was a hard limit, a wall we could never look over.
He did.
Yeah.
In fact, there's a really famous, almost infamous example of this. The French philosopher Auguste Comte.
Okay.
In 1835, he was writing about the limits of scientific knowledge. And this is just, a couple of decades before the big breakthrough.
So he's right on the cusp of it.
Right on the cusp. And he confidently stated that while we might one day determine the distance, the motion, and maybe even the mass of stars.
All the physical properties.
Right. The geometry of it all. But he said we would never, by any means, be able to study their chemical composition.
He essentially said, don't even bother trying. It's impossible.
He laid it down as a fundamental epistemological wall. He said, the stars are there and we are here.
And the gap is just too big.
The only thing that bridges that gap is light. And back then, light was just brightness. It was illumination. It wasn't seen as a carrier of data.
It wasn't information. It was just light.
Exactly.
It's so funny because looking back, the clues were there all along, but the whole mindset, the whole worldview just wasn't ready for it.
Oh, completely. You had brilliant ancient astronomers. They could predict eclipses with stunning accuracy. They tracked the planets. They navigated the oceans by the stars. They were masters of the geometry of the sky.
But the question of what is that light actually made of?
That wasn't science. That was philosophy or religion.
Right. You had the old Aristotelian view, which dominated for centuries.
The idea that the heavens were made of something totally different, ether.
Celestial matter.
Yeah, this perfect, immutable fifth element. The whole idea was that Earth is corrupt, it's heavy, it's changeable, but the heavens are perfect and eternal.
So the idea that the sun might be made of the same, I don't know, sodium that's in my table salt,
That would have been heresy, or at the very least, scientific nonsense.
it wouldn't compute.
It would be like saying a cloud is made out of solid marble. The categories just didn't fit the worldview.
Okay, so to crack this impossible code, we have to start with the detective story of light itself. And the main character in our first act is a man whose life story is, it's just incredible. Joseph von Fraunhofer.
Fraunhofer is a fascinating figure. He was not born into academia or privilege, not at all.
He was a craftsman.
He was. Born in 1787 in Bavaria, the 11th child of a glazier.
The 11th child.
And he was orphaned by age 11. He gets apprenticed to this mirror and glass maker in Munich who treated him terribly.
I read he was basically a slave laborer.
That's a fair description.
Yeah.
He wasn't allowed to go to school. He wasn't allowed to read books. The master saw any kind of education as a threat.
And then the incident happens, the huge turning point in his life.
The workshop he was living in collapsed. The whole building just crumbled to the ground with him inside.
Wow.
It was a massive disaster in Munich at the time. A huge rescue operation started. But here's the twist of fate that changes everything.
Okay.
The local ruler, Prince Maximilian Joseph, who would later become the King of Bavaria, happened to be in the crowd that gathered to watch the rescue effort.
Talk about a stroke of luck in the middle of a catastrophe.
It's unbelievable.
Yeah.
And when Fraunhofer was finally pulled from the rubble, hours later, he was the only survivor.
The only one.
The prince was so moved by this, he took a personal interest in this miraculous survivor. He gave him a sum of money, and crucially, he arranged for him to get books and time to study. He essentially bought out his apprenticeship.
So the man who ends up unlocking the chemical secrets of the stars starts his journey by almost being crushed to death by a building.
It's the most unlikely origin story. And because his apprenticeship was bought out, he was able to get a real job at a scientific and optical institute.
Right. And he wasn't a theoretical physicist. He was obsessed with the practical stuff.
He was obsessed with quality, specifically the quality of glass. He wanted to make the most perfect prisms and the most perfect telescope lenses in the world.
And at the time, glass was not great.
It was full of imperfections, bubbles, streaks, what they call striae. These flaws would ruin the image, making it blurry or distorted.
So he's working on this. He's trying to make perfect glass. How does this lead him to the sun?
Well, he needs a standardized, consistent source of light to test his lenses. Something bright and always the same. What's brighter and more consistent than the sun?
Good point.
So it's 1814. He takes a beam of sunlight, passes it through a very narrow vertical slit to get a clean line of light, and then he shines that through one of his new super high-quality prisms.
Now, Isaac Newton had done this more than a century earlier.
Right. And Newton saw the rainbow. Red, orange, yellow, green, blue, violet. A continuous smear of color, a spectrum.
But because Fraunhofer's setup was so much better,
His glass was clearer and his slit was much narrower. He saw something that Newton had completely missed.
he saw that the rainbow wasn't perfect.
He wasn't perfect at all. It was riddled with holes.
Holes, like black spots.
Dark lines. Hundreds of them.
Ah.
Thin, vertical black slivers where the light was just gone. It wasn't a continuous spectrum. It was sliced up, like a barcode.
And his first reaction must have been,
Damn it, my glass is flawed.
he thought they were scratches or something.
He was a perfectionist. He thought it was an error. So he checked everything. He polished the glass again. He changed the prism. He adjusted the angle of the light.
But the lines stayed.
They stayed. And here's the crucial observation. They're always in the exact same place. He found a very distinct dark line in the orange part of the rainbow. He found a pair of very close together dark lines in the yellow. He saw thick, chunky ones in the blue and violet.
They weren't random smudges. They were fixed and repeatable.
Absolutely. So he realized they weren't flaws in his equipment. They were a real property of sunlight itself.
And he didn't just see a few of them, right?
No, he meticulously mapped over 570 of them. He gave the most prominent ones letter designations, just so he could refer to them. The A line, the B line, the C line.
And you mentioned that pair of lines in the yellow.
He called them the D lines. That detail becomes incredibly important later.
But here's the kicker, the tragic part of his story. He had no idea what they were.
Absolutely no clue. He died relatively young, in his 30s, from tuberculosis. He never knew that he had just discovered the chemical barcode of the entire universe.
So what did he use them for?
For him, they were just incredibly precise reference points. He could use the D lines, for example, to measure the refractive index of his glass for yellow light with unprecedented accuracy. They were a tool for his craft.
That's amazing. He finds the Rosetta Stone of light, and he uses it to build a better pair of glasses.
It's the ultimate tragedy of a scientist being ahead of his time. He found the key, but the lock hadn't been invented yet.
So we need to invent that lock. Fast forward about 45 years, we need to get from these mystery lines to chemical composition.
Right.
And this brings us to the dynamic duo of the 1860s in Heidelberg, Germany, Gustav Kirchhoff and Robert Bunsen.
Yes, Bunsen, of the famous Bunsen burner.
I feel like every high school chemistry student knows that name, but they just think of him as the guy who invented a piece of lab equipment. They don't realize he was a world-class scientist.
Oh, he was brilliant, a true experimental genius. And he actually invented the burner for a very specific reason related to our story. He needed a clean flame. See, the alcohol lamps and other burners they were using before were sooty and bright yellow. The color of the flame itself would interfere with the light of whatever he was trying to burn.
So he needed a flame that was basically hot and invisible.
Exactly. So he could see the pure color of the chemicals he was testing.
Okay, so they're in their lab in Heidelberg. They have this new, clean burner. What's the core experiment they're doing?
They were doing something very systematic. They would take purified chemical salts, things like sodium chloride, which is table salt, calcium chloride, lithium chloride.
All the different elements.
All the different elements they could get their hands on. They'd dip a little platinum wire into the powder and then stick it into the hot, colorless flame of the Bunsen burner.
And then they would look at the light from that flame through a prism.
Right. Just like Fraunhofer did with sunlight, but the result was completely different.
Instead of a full rainbow with some dark lines.
They saw the exact opposite of a rainbow. When you burn pure sodium, you don't get a smear of colors. You get two incredibly bright, sharp, vivid yellow lines.
And the rest of the spectrum is just black.
Pitch black. This is what's called an emission spectrum. The hot gas is emitting light, but only at very specific wavelengths.
And it was different for every element.
It was a unique fingerprint. When they burned lithium, they got a brilliant red line. Strontium gave them a different shade of red. Hydrogen, when they put it in a glass tube and zapped it with electricity, gave them a very specific pattern, a red line, a blue-green line, and a couple of violet lines.
So they realized that every single element has its own unique, unchangeable spectral signature.
Yes. Sodium always makes that yellow double line. It never makes a red line. It never makes a blue line. If you see that specific yellow doublet, you're looking at sodium. It's an unbreakable rule of nature.
Okay, so they have this growing library, this catalog of bright line fingerprints from earthly elements. How do they connect this back to the sun?
This is the moment. This is the linchpin where the whole detective story comes together, and it's thanks to Kirchhoff.
What did he do?
He took the spectrum of the burning sodium from their lab, those two bright yellow lines, and he projected it right next to Fraunhofer's map of the solar spectrum, the one with all the dark lines.
A map with the dark D lines and the yellow.
Exactly. And he saw something that must have just given him chills.
The lines matched up.
They didn't just match up. The bright yellow lines of sodium from the lab fell exactly, and I mean to the nanometer, perfectly into the dark D lines that Fraunhofer had mapped in the sun spectrum 60 years earlier.
The bright lines filled the dark holes.
It was a key fitting perfectly into a lock. It was undeniable.
So Kirchhoff realizes... What?
He realizes that the dark lines in the sun's spectrum are caused by sodium atoms. The sun contains sodium.
Okay, I need to pause on this because this is the absolute crux of the whole thing. It seems counterintuitive.
That is.
In the lab, the hot sodium gas makes bright yellow lines. But in the sun, the sodium atoms make dark yellow lines. Why the flip? Why is it emitting in one case and stealing in the other?
That is the brilliant insight that Kirchhoff had. It's the difference between an emission spectrum and an absorption spectrum.
Explain that.
In the lab, the hot sodium gas is glowing against a dark background, so it's the source of light. It emits those yellow photons. But think about a star. A star isn't just a cloud of hot gas.
It has layers.
It has layers. You have a super hot, dense core, the photosphere, that's so hot and dense it's creating a continuous rainbow. It's the light bulb.
Okay, so the core makes a perfect rainbow with no lines at all.
Exactly. But then that perfect rainbow of light has to travel outward through the cooler, less dense outer layers of the star's atmosphere, the chromosphere.
And that's where the sodium is.
That's where the sodium atoms are just hanging out. They're cooler than the core. And they act like a filter.
A filter.
They're like little thieves. A sodium atom sees that flood of rainbow light coming from below, and it sees those specific yellow photons. that have the exact right amount of energy it likes to absorb. And it says, I'll take that. And it snatches it out of the beam.
It absorbs it.
It absorbs it. So by the time that beam of light has passed through the star's atmosphere and traveled 93 million miles to Earth, those specific yellow wavelengths have been removed,
Leaving a dark gap where they used to be?
leaving Fraunhofer's dark lines.
So the dark lines are essentially the shadows cast by the atoms in the star's atmosphere.
That is a beautiful and perfect way to put it. They are atomic shadows. And once Kirchhoff figured this out, the floodgates just opened.
They could start matching everything.
Everything. They pointed their spectroscope at the sun and said, okay, that dark line matches the bright line of iron in our lab. The sun has iron. That one matches calcium. The sun has calcium, magnesium, chromium, nickel.
They proved, once and for all, that the sun wasn't made of some magical ether.
It was made of the exact same stuff from the periodic table that we have right here on Earth.
Auguste Comte was completely and utterly wrong.
Couldn't have been more wrong. They had bridged the gap.
Okay, so we know that it works. We have the code and the key. But I really want to understand why it works on a fundamental level. Why does sodium only steal that specific shade of yellow? Why does hydrogen only care about that one red and that one blue-green light?
Now you're asking the quantum question.
This gets us into the structure of the atom itself.
It does. And we have to be a little careful here because the simple model of the atom, we all learn in grade school.
The little planetary system with electrons orbiting the nucleus like tiny moons.
Right. That model is useful, but it's not quite right. A better analogy, and the one physicists often use, is a ladder.
The quantum ladder.
The quantum ladder. The key idea is this. In our everyday world, if you have a ramp, you can stand anywhere on it. You could be 1 foot off the ground, or 1.5 feet, or 1 foot and 1.37 inches. It's continuous.
I can have any amount of potential energy I want.
Exactly. But inside an atom, energy is not continuous. It is quantized. It comes in discrete packets. So an electron's energy levels aren't a ramp. They're the rungs of a ladder.
So an electron can be on rung 1, or it can be on rung 2, but it cannot hover in the space between the rungs.
It is physically forbidden. It cannot exist there.
Okay, so we have these allowed energy levels, these rungs. What happens next?
Well, electrons, like most things in nature, are lazy. They want to be in the lowest possible energy state. They want to be on the bottom rung, which we call the ground state.
But if you add energy to the atom, like you heat it up in a star's core or zap it in a Bunsen burner,
you're kicking that electron. You're giving it a jolt of energy, and it has to do something with it. So it jumps.
it makes a quantum leap, as they say.
It makes a quantum leap up to a higher unoccupied rung on the ladder. Let's say it jumps from level 2 up to level 3.
But that's an excited state, right? It's unstable.
Highly unstable. Nature hates high energy instability.
Hmm.
So almost instantly, within nanoseconds, that electron is going to fall back down to its original, more comfortable level.
It falls back down from rung 3 to rung 2.
Yes. And the energy it absorbed to make the jump up has to be released. Conservation of energy.
And it's released as light?
It is released as a single packet of light, a photon. And here is the absolute magic of the whole system. The color of that photon, its wavelength, is determined strictly and precisely by the distance of the fall.
So a big drop from a high rung to a low rung.
A long fall is a lot of energy. That releases a high-energy photon, which our eyes perceive as blue or violet or even ultraviolet light.
In a short drop.
A short little hop between two closely spaced rungs releases a low-energy photon, which we see as red or orange or infrared light.
And the reason every element has a unique fingerprint is because their ladders are built differently.
Exactly. Every element has a different number of protons in its nucleus, which creates a different electrical field, which in turn means the spacing of the electron energy rungs is completely unique to that element.
So the ladder for hydrogen looks totally different from the ladder for helium or iron.
Totally different. So the possible jumps an electron can make are unique. For a hydrogen atom, the drop from rung number 3 down to rung number 2 always releases a photon with a wavelength of exactly 656.28 nanometers.
That's the famous red Balmer alpha line I've seen mentioned everywhere.
That is its calling card, that specific shade of deep red. If you see light at 656 nanometers, You are, without a doubt, looking at hydrogen.
And for sodium, that yellow D line corresponds to a specific small jump.
A very specific, very common jump an electron in a sodium atom likes to make. It always spits out a photon with a wavelength of 589 nanometers.
So it's absolute. It's a physical constant of the universe.
It is. The universe is broadcasting the chemical composition of everything in it in high fidelity. We just needed to build the right receiver to tune in.
And that receiver is the spectroscope.
That's the one.
Okay, so we have the tool. We understand why it works. We pointed at our sun. What did we find? I know we said it's made of the same stuff as Earth, but the proportions were a complete shock, weren't they?
A massive paradigm-shifting shock. Based on the old Aristotelian celestial matter idea, people might have expected something exotic, like gold or some unknown element.
Or if you went with the Earth and heaven are the same idea, you might expect it to be like a big rock.
Right. You'd expect to see lots of silicon and oxygen and iron, the stuff that makes up the Earth's crust.
But the sun is not a giant glowing rock.
Not even close. When the analysis was finally done, and this was largely the work of a brilliant astronomer named Cecilia Payne-Gaposchkin in the 1920s.
Her work was famously suppressed for a while, wasn't it?
It was. Her doctoral thesis concluded that the sun was overwhelmingly hydrogen. The leading male astronomer at the time told her it was clearly impossible and made her remove it. Of course, he published a paper a few years later saying the same thing and realized she was right all along.
A classic story, unfortunately. So what were her numbers?
She found that the sun is almost entirely hydrogen. By mass, it's about 73.4% hydrogen.
Okay. And the rest?
The next biggest chunk is helium, at about 24.8%.
Wait, so let me do the math. That's 98.2% of the sun is just the two lightest, simplest gases in the universe.
That's it. Everything else is just a trace contaminant.
And speaking of helium, there's a crazy story there too, right?
There is. It's one of my favorite bits of science history. We actually discovered helium in the sun before we ever found it on Earth.
How is that even possible?
During a total solar eclipse in 1868, the astronomer Pierre Janssen was looking at the spectrum of the sun's atmosphere. He saw a bright yellow line that he couldn't identify. It wasn't the sodium D lines. It didn't match anything known on Earth.
A mystery line.
A complete mystery. Another astronomer, Norman Lockyer, proposed that it must be a new element, unknown on Earth, that only existed in the sun.
And he named it.
He named it helium, after Helios, the Greek god of the sun.
But people must have thought he was crazy.
They did, for about 30 years. Until, in the 1890s, a chemist was analyzing a uranium-bearing mineral and found it was giving off a strange inert gas. When he put that gas into spectrometer, there it was, the same bright yellow line.
That is wild. We discovered an element on a star 93 million miles away before we found it trapped in rocks under our own feet.
It just shows you the incredible power of spectroscopy. But back to the sun's composition. We've got our 98% hydrogen and helium. That leaves less than 2% for everything else combined.
And this is where we get to that weird astronomical jargon.
Yes, the bit that drives chemists insane.
To an astronomer, anything that isn't hydrogen or helium is a metal.
Right. To us, oxygen is a metal. Carbon is a metal. Neon is a metal. It's a lazy but very useful shorthand.
So what's in that tiny sliver of metals?
That little 1-point-something% contains all the good stuff. The most abundant metal is oxygen, at about 0.77% of the sun's mass.
Still less than 1%.
Right. Then you have carbon at about 0.29%. Iron and neon are tied at around 0.16%. Nitrogen at 0.09%, and then it just goes down from there. Silicon, magnesium, sulfur.
So even though iron is crucial for life on Earth, in the grand scheme of the sun's composition, it's just a tiny contaminant.
A rounding error. But this leads to the most profound realization of all. The universe, in its initial state, only creates the simple stuff. The hydrogen and helium are primordial. They are the leftovers from the Big Bang.
But all the heavy stuff.
All the heavy stuff. The carbon in your DNA, the oxygen you're breathing right now, the iron in your blood.
Yeah.
That had to be made. It had to be forged somewhere.
And that somewhere brings us to the cosmic kitchen. The process of nucleosynthesis inside stars.
Exactly. Because the Big Bang didn't make that stuff, did it?
No. From what I've read, the Big Bang was incredibly hot and dense, but it expanded and cooled down way too fast.
It was like trying to bake a cake in a flash fire. It only had a few minutes to do any cooking at all.
And in those few minutes,
it managed to fuse some hydrogen into helium, and it made a tiny, tiny pinch of lithium. And that's it. The ovens shut off.
So for the first few 100 million years, the entire universe was chemically barren.
Unbelievably boring. You couldn't make a planet. You couldn't make a rock. You couldn't make a molecule of water. There were no ingredients.
So where did the ingredients for Earth and for us come from?
They came from the first generations of stars. Stars aren't just giant passive light bulbs. They are active fusion reactors. They are Archimed's furnaces.
So walk us through it. How does a star turn simple gas into, say, carbon or oxygen?
It all starts in the core. The immense gravity of the star is crushing everything down. The pressure is astronomical, and the temperature is millions of degrees.
Hot and dense enough to overcome the natural repulsion between protons.
Exactly. So the star starts by taking hydrogen nuclei, which are just single protons, and smashing them together so hard that they stick. It fuses 4 hydrogen atoms into 1 helium atom.
And that process releases a huge amount of energy.
A tremendous amount. That's why the star shines. That energy pushes outward, fighting against the inward crush of gravity, and keeps the star in a stable balance for billions of years.
Okay, so that explains where the extra helium comes from. But how do we get to the heavier stuff?
Eventually, for a star like the Sun, the hydrogen fuel in the core starts to run out. The core becomes mostly helium ash.
So it's filling up with its own waste product?
Right. But if the star is massive enough, significantly more massive than our, sun gravity doesn't give up. It squeezes that helium core even tighter. The pressure and temperature skyrocket to over 100 million degrees.
And now it starts fusing the helium.
Now it starts to burn the ash. But this is a much harder trick to pull off. To make carbon, you need to smash 3 helium nuclei together at almost the exact same instant.
This is the triple alpha process, right?
That's the one. It's called that because the helium nucleus is also known as an alpha particle.
And I read that this is a huge bottleneck in the universe. It's almost impossible.
It's a massive bottleneck because if you just smash 2 helium nuclei together, you get beryllium-8. And beryllium-8 is incredibly unstable. It falls apart back into 2 heliums in a fraction of a quadrillionth of a second.
So you have this impossibly short window to hit it with a 3rd helium nucleus to make stable carbon-12.
It's a miracle of physics that it happens at all. The fact that the universe manages to bridge that gap and create carbon is one of those amazing, fine-tuned properties of our reality. But it happens. Stars do it.
So we've made carbon. What's next?
Once you have carbon, it gets a bit easier. The star can then fuse a helium with a carbon to make oxygen, then a helium with an oxygen to make neon.
So it's building the periodic table layer by layer.
Like building layers of an onion. In the core of a very massive dying star, you'll have a core of silicon and sulfur, surrounded by a shell of oxygen burning, surrounded by a shell of neon, then carbon, then helium, and a big outer envelope of hydrogen.
But there's a wall coming, isn't there? A hard stop. The Iron Peak.
The Iron Peak. This is one of the most dramatic and important limits in all of nuclear physics.
Why does everything stop at iron? Why can't a star just keep fusing heavier and heavier elements forever?
It all comes down to a concept called binding energy per nucleon. It's a measure of how tightly packed and stable an atomic nucleus is.
Okay.
Up until you get to iron, every time you fuse 2 lighter atoms together to make a heavier one, the resulting nucleus is more stable. It's lighter than the sum of its parts.
And that missing mass is converted into pure energy thanks to Einstein.
E equals mc squared. Fusion pays you energy. It releases heat and light. That outward radiation pressure is what holds the star up against gravity.
It's paying the cosmic rent.
It's paying the rent. But iron-56 is the most tightly bound, most stable nucleus in the entire universe.
Yeah.
It is the absolute bottom of the energy valley.
So what happens if you try to fuse iron into something heavier, like zinc?
You have to put energy in. It doesn't release energy, it consumes it. It steals heat from the core.
So the moment a massive star's core turns to iron,
the rent check bounces. The furnace at the heart of the star doesn't just turn down, it switches off and turns into a refrigerator.
The outward pressure vanishes.
Instantly. And gravity, which has been patiently waiting for millions or billions of years, finally wins.
And that's the collapse.
A catastrophic, unbelievably violent collapse. The iron core, which might be the size of the entire Earth, collapses down to the size of a city in less than a second.
And the outer layers?
The outer layers come screaming inward, crash into this newly formed, super dense neutron core, and rebound in a titanic explosion we call a Type II supernova.
And that explosion is absolutely crucial for us.
It's the delivery mechanism. It's everything. Without that supernova explosion, all that precious carbon, oxygen, and silicon would be locked away inside a dead star forever.
But the explosion blasts it all out into the galaxy.
It enriches the interstellar medium. It seeds the next generation of gas clouds with the heavy elements needed to build planets and people.
But wait a second. If fusion inside stars stops at iron, where does all the stuff heavier than iron come from? Where does the gold, the silver, the platinum, the uranium, where is that made?
That requires a level of violence that makes even a supernova look tame. For the heaviest elements, you can't use fusion. You need neutrons. Lots and lots of neutrons.
This is the R process I've heard about.
The rapid neutron capture process. Yes. Imagine you have a seed nucleus, like an iron atom. You want to make it heavier.
So start adding neutrons to it.
Right. But the problem is, as you add neutrons, the nucleus often becomes radioactive and unstable. It beta decays. A neutron turns into a proton, and it changes into a different element before you can add more neutrons.
So to make something really heavy like gold or uranium,
You have to bombard that seed nucleus with an insane flood of neutrons. You have to slam them in there so fast, hundreds of thousands of times per second, that the nucleus puffs up into this massive, bloated, neutron-rich monster before it has a chance to decay.
and where in the universe do you find an environment like that?
For a long time, we thought it happened in supernovae. But recently, we found a much better candidate, the collision of two neutron stars.
So you take two city-sized objects, each more massive than our sun, made of pure nuclear density matter, and you slam them into each other at a fraction of the speed of light.
That's the event, a kilonova. When they collide, they shred each other apart and spray out this incredibly dense, neutron-rich material. That is the ultimate forge for the heaviest elements.
So when I look at a piece of gold jewelry,
You are looking at the shrapnel from a collision of two dead stars that happened billions of years ago.
that puts a whole new spin on a wedding ring. It's not just a shiny metal, it's the debris from one of the most violent events in the cosmos.
It truly is. And there's also a slow process, the S process, that happens in some dying giant stars, and that makes elements like barium and lead. But the really precious heavy stuff, that requires pure cosmic violence.
So we have this amazing cosmic cycle. Stars are born from gas clouds, they cook new elements in their cores, they die, they explode, and they enrich the next generation of gas clouds.
It's the ultimate recycling program.
And this leads us to a really cool field, stellar archaeology.
I love that term. It's exactly what we do. We're digging through the ruins of the past by looking at the chemistry of stars that are still alive today.
And the main tool for that is metallicity, right?
Correct. And again, we're using the astronomers' weird definition of metal.
Anything heavier than helium.
Right. So think about it. When the galaxy was very young, just after the Big Bang, the gas clouds were pristine. They were clean.
Just hydrogen and helium.
Exactly. So the very first stars that formed, what we call population third stars, they must have had a metallicity of basically zero.
And we've never seen one of those, have we?
We never have. They were all incredibly massive and lived very short lives, exploding long ago. But the stars that formed from their ashes, the next generation,
They would have a tiny bit of metal.
a tiny bit, and then they die and pollute the gas a little more. So stars that form today, like our sun, are forming from gas that's been recycled through countless generations of supernovae.
It's dirty, metal-rich gas.
So we have a clock. If we look at a star and find that it has lots of iron and oxygen, we know it's a relatively young star, a modern kid on the block.
And if we find a star with almost no iron at all,
Then we know we're looking at an ancient relic, a fossil from the early days of the galaxy.
and we can use this to map the galaxy's history.
We can. The Milky Way has a flat, spinning disk. That's where we live.
Mm-hmm.
And it's surrounded by a big, puffy, spherical halo.
And the stars in the halo are different.
The stars in the halo are incredibly metal poor. They're the dinosaurs. They're the old ones who formed before the disk really got going. The stars in the disk, like the sun, are the young ones, living in the rich, polluted environment created by their ancestors.
It's like looking at the different neighborhoods of a city and seeing its history.
And we can even see evidence of galactic cannibalism. We see streams of stars in the halo that have a slightly different chemical fingerprint, which tells us they used to be part of a smaller galaxy that the Milky Way ate billions of years ago.
It's all written in the light.
It really is.
Okay, I want to pivot for a second to the actual toolbox we use. We've talked about Fraunhofer and his simple prism, but modern astronomers aren't holding a little glass triangle up to their eye. What does a modern spectrograph look like?
It's a whole different beast. A modern spectrograph is a massive, complex instrument. It can be the size of a car or even a small room attached to the back of a giant telescope.
And instead of a prism,
It uses something called a diffraction grating. It's a surface etched with thousands of incredibly fine parallel lines. It's much, much more efficient at splitting light into its constituent colors than a prism.
So it creates a really long, detailed rainbow.
It can stretch the spectrum out so far that we can split it into hundreds of thousands of tiny color channels, or bins, and measure the brightness in each one. And instead of our eyes, we use super-sensitive digital detectors called CCDs, the same technology that's in your phone camera, but cooled to cryogenic temperatures.
Wow.
They can literally count individual photons of light coming from a star on the other side of the galaxy.
But the light tells us more than just composition, right? We can measure a star's speed.
Oh, absolutely. The Doppler shift. There's a huge part of modern astronomy.
It's the same principle as a siren on an ambulance.
Exactly. When the ambulance is coming towards you, the sound waves get compressed and the pitch sounds higher. When it moves away, the waves get stretched out and the pitch sounds lower.
And the same thing happens with light?
The exact same thing.
Yeah.
If a star is moving toward us, its entire spectrum, all those dark Fraunhofer lines, gets shifted slightly toward the blue end of the spectrum. We call it a blue shift.
And if it's moving away, it's a red shift.
A red shift. And the amount of the shift tells us the speed. And the precision we can achieve today is just mind-boggling.
How precise?
For nearby bright stars, we can detect a change in velocity of about 1 meter per second.
That's walking speed.
That's a slow walking speed. We can tell if a star millions of miles away is moving toward or away from us at the speed you walk down the hallway.
And that's the technique we use to find planets around other stars, isn't it?
It's one of the main ones. The radial velocity method.
How does that work?
Well, if a star has a massive planet orbiting it, like a Jupiter, the planet doesn't just orbit the star. They both orbit their common center of gravity.
So the planet is actually tugging on the star, making it wobble.
It makes the star do a little dance. It wobbles back and forth. So from our perspective on Earth, sometimes the star is moving slightly toward us in its wobble, and sometimes it's moving slightly away.
And we can see that tiny wobble in its spectrum.
We see the whole barcode of spectral lines shifting back and forth in a periodic way. We can't see the planet at all, but we can see the gravitational effect it has on its star.
And the size of the wobble tells us how massive the planet is.
Exactly. It's how we found the very first exoplanets back in the 90s, and it's still one of our most powerful tools.
Okay, so we've covered how we do it. And all of this data has allowed us to create a classification system for stars. You can't get through an Astronomy 101 class without memorizing a weird sequence of letters.
O, B, A, F, G, K, M.
And the famous mnemonic.
Oh, be a fine girl, kiss me. Or guy. Or gorilla. There are many, many versions.
What do those letters actually mean? What are we classifying?
It's fundamentally a temperature scale, from hottest to coolest. It was originally developed by looking at the strength of the hydrogen lines, but we later realized that was really a proxy for temperature.
So O stars are the hottest?
O stars are the hottest. They are absolute monsters. Surface temperatures over 30,000 Kelvin. They are brilliant blue-white, incredibly massive, and they live very short, violent lives.
They burn through their fuel really fast?
Like an SUV with a hole in the gas tank, an O star might only live for a few million years before it explodes as a supernova.
And at the other end, we have the M stars.
The M dwarfs, or red dwarfs. These are the coolest, smallest, faintest, and by far the most common stars in the galaxy.
They sip their fuel.
They sip it so slowly. A red dwarf can live for trillions of years, far longer than the current age of the universe. They are the ultimate survivors.
And where does our sun fit in?
Our sun is a G-type star, specifically a G2V. It's right in the middle of the pack. A nice, stable, yellow-white star with a surface temperature of about 5,800 Kelvin.
It's kind of boring.
It's wonderfully, blessedly boring.
Yeah.
Which is exactly what you want if you're trying to evolve complex life on a nearby planet.
Right. You don't want your star having temper tantrums or, going supernova while you're still trying to invent photosynthesis.
Stability is key.
This brings us to the real so what factor. We've gone over the history, the quantum physics, the stellar fusion. But why does this all matter to the person listening right now, beyond just, wow, science is cool?
Well, it matters because it connects us to the cosmos in a literal, physical way that is just inescapable once you see it.
Let's start with the planets.
Okay, the planet connection.
Yeah.
Through our exoplanet surveys, we have found a very strong, very clear correlation. Stars with high metallicity are much, much more likely to have giant Jupiter-like planets orbiting them.
And the logic there is you need the raw materials.
You need the raw materials. The current theory of planet formation says that to build a gas giant like Jupiter, you first need to build a solid core of rock and ice, about 10 times the mass of the Earth.
A seed.
A seed. And then that massive seed can gravitationally attract a huge atmosphere of hydrogen and helium gas. But if you start with a primordial gas cloud that is only hydrogen and helium,
There's no rock, there's no dust, there's no ice.
you can't build the seed. So we live in a solar system with planets because our sun is a polluted star. It formed from a cloud that was enriched with heavy elements from previous generations of dead stars.
So we are quite literally the beneficiaries of cosmic pollution.
Yes, we owe our existence to it. If the sun had been a first-generation star, Earth would not exist. This would just be a gas cloud.
And then there's the even more direct connection, the one that's inside our own bodies. The famous phrase, we are stardust.
It's a phrase that gets thrown around a lot, most famously by Carl Sagan, and it can sound like a nice metaphor. But I want to really unpack the literal physical truth of it.
Okay, let's trace it. Let's take a single iron atom in my blood.
Okay, that one specific iron atom in a hemoglobin molecule, which is carrying oxygen to your brain as we speak, that atom was not created on Earth. It was not created in the sun. It was forged in the unimaginably hot and dense core of a very massive star, probably at least 20 times the mass of our sun, that lived and died billions of years ago.
It sat inside that stellar furnace, witnessing temperatures of billions of degrees.
And then that star's life came to an end. It built up an iron core, the fusion stopped, it collapsed, and it exploded in a supernova.
And that one specific iron atom was blasted out into the galaxy?
Ejected at thousands of miles per second. It then drifted through the cold, empty void of interstellar space for eons, for maybe millions, maybe billions of years.
Just floating.
Until, by chance, it got caught in the gravity well of a condensing cloud of gas and dust, the solar nebula that would become our solar system.
It became part of the raw material for the planets.
It became a speck of dust that clumped together with other specks to form the planet Earth. It sank into the molten core, maybe got cycled up to the crust through a volcano, became part of a rock, eroded into soil.
Got taken up by a plant that was eaten by an animal, or by me.
And now, after a journey of billions of years and trillions of miles, it is in your bloodstream, performing a vital biological function.
That is humbling, to say the least.
And it's not just the iron. The calcium in your bones and teeth, forged in a star, the carbon in your genes, the nitrogen in your DNA, the oxygen you're breathing, all of it is stellar debris.
We are not just in the universe, we are literally of the universe.
We are the mechanism by which the universe has become self-aware. We are the cosmos observing itself.
It completely dissolves the separation between us down here and space up there.
There's no separation. It's a continuous chain of cosmic creation and recycling.
So as we start to wrap up, what's the future of this field? It sounds like we've mapped the elements pretty well. Are we done?
Oh, not even close. We are entering what many people think of as a new golden age of spectroscopy. We are building the next generation of telescopes.
Like the ELT, the extremely large telescope.
Astronomers are very, very literal with their names.
I've noticed.
The ELT will have a primary mirror that is 39 meters across. For context, the biggest telescopes operating today are in the 8 to 10 meter class. This thing is an absolute beast.
And what will that let us do?
It'll gather so much light that we'll be able to do high-resolution spectroscopy on individual stars in other nearby galaxies, not just our own Milky Way.
So we can start doing stellar archaeology on our galactic neighbors.
Exactly. We can compare the chemical history of the Andromeda Galaxy to our own. And we're also bringing new tools to bear, like artificial intelligence.
How does AI help?
We have sky surveys, like the Gaia mission, that are collecting spectra from hundreds of millions, soon to be billions of stars. No single human, or even a team of humans, can look at all that data.
It's just too much.
It's a deluge. So we're training machine learning algorithms to sift through it all, to find the weirdos. The chemically peculiar stars, the stars that don't fit our models, the ones that might have eaten a planet or come from a different galaxy. The AI can find patterns we would miss.
And there's one more technique I wanted to ask about before we finish. Astroseismology.
Starquakes.
Starquakes. How on earth does that work?
It is so cool. It's basically like performing an ultrasound on a star. The boiling convective motions inside a star create sound waves that bounce around inside it.
And those sound waves make the surface vibrate.
They make the surface of the star vibrate or oscillate, causing its brightness to change in very tiny but very regular and rhythmic patterns.
And by analyzing those rhythms,
we can work backward and figure out the density, the temperature, and the structure of the star's deep interior, including the core itself.
So spectroscopy shows us the chemical composition of the star's skin, and astroseismology lets us see the guts.
That's a perfect analogy. It lets us directly test our models of nuclear fusion. It confirms that the engines inside stars are running exactly how the nuclear physicists on Earth predicted they would. It's an incredible confirmation of our theories.
It's just amazing how we keep finding new ways to sense the universe. First, it was just our eyes, then it was glass lenses, then prisms, now we're using sound waves and AI.
And every time we develop a new sense, a new way to look, we find that the universe is even more intricate and more connected than we thought.
So to bring it all home, we started this discussion with what seemed like an impossible problem. How do you know what something is made of when you can never, ever touch it?
And the answer, it turned out, was that we don't need to go to the stars. The stars are constantly sending their autobiography to us every second of every day.
An autobiography written in the barcode of light.
Exactly.
We learned that those dark lines Fraunhofer saw are the atomic shadows, the fingerprints of the elements. And we learned that all the elements heavier than helium are the ash from stellar furnaces and the debris from cosmic collisions.
And most importantly, we learned that those ancient violent histories are the direct and literal cause of our own existence.
So here's my final thought for everyone listening. The next time you hold a piece of gold, a coin, or maybe the ring on your finger, don't just see a shiny, inert piece of metal. Try to actually visualize the cataclysmic collision of two neutron stars that forged those atoms billions of years ago. Visualize their impossible journey across the void to become part of our world. It fundamentally changes how you see everyday objects.
It really does. It's all stardust.
And the next time you happen to see a rainbow, maybe after a storm, remember Joseph von Fraunhofer. Remember that it's not just a pretty arc of colors. It's the key that unlocked the library of the entire universe.
It's the barcode of reality.
Thanks for listening. Stay curious and keep looking up.